of course be used as generative models as well. They can generate text, image and video, and even audio and speech. Foundation models are often used as the base and then can be further fine-tuned for specific tasks. A foundation model can be adapted to more targeted systems based on what exactly the end user is looking for. For example, OpenAI's ChatGPT model uses one of the GPT models as the foundation models, either 3.5 or 4, and it has been further fine-tuned to follow instructions using supervised fine-tuning and reinforcement learning from human feedback, RLHF. RLHF is a machine learning approach which combines a technique called reinforcement learning with human feedback to guide AI models towards desired behaviors. And we'll talk more about that in just a bit. And it is this additional task-specific fine-tuning that allows ChatGPT to function as well as it does. ChatGPT performed better than foundation models. It had a higher accuracy in its responses, less toxic sentiment, and proved to be better aligned with user needs, all because of the additional fine-tuning and learning from human feedback. Let's quickly discuss the training data that was used for the different GPT foundation models. GPT-1, released back in 2018, could generate fluent and coherent language when given a prompt or context, and it was a very powerful model of its time. It was trained using the book corpus dataset with 7,000 unpublished books. However, the GPT-1 model had several flaws. It would often generate repetitive text. It could not reason with you when you're having a conversation, and it could not track long-term dependencies in text. It was hard for it to have a back and forth conversation and remember all of the previous context. GPT-2 was of course a more powerful model with many more parameters, and the model could generate coherent and realistic sequences of text and much longer sequences at that. Now this was trained on the WebText dataset containing 8 million documents from 45 million web pages uploaded on Reddit. However, this too had its drawbacks. It struggled with more complex reasoning and understanding of context. The bigger and better GPT-3 came along in 2020, and this was a far more powerful model. It could generate coherent text, it could write code, it could create art, it understood context and used the context to generate its responses. The training data for GPT-3 is also very diverse. It includes the Common Crawl dataset, that is data from the web, to Book Corpora, web text, and the English Wikipedia. However, this model too had its own set of flaws. The model often returned biased, inaccurate, or inappropriate responses. At the time of this recording, the latest in the GPT series of models is GPT 3.5 and GPT 4 that power the current version of ChatGPT. There is no information available about the data used to train the model, since there is no peer-reviewed paper that has been released. As models are scaled to be larger and are trained on even larger corpora of data, GPT-4 has an estimated 1.7 trillion parameters. There is an important concept that we should talk about, and that's emergence. Emergence refers to the phenomenon where complex and often unexpected behaviors or capabilities arise from simpler underlying structures as the scale or complexity of the model increases. Emergence describes how complex patterns, abilities, or behaviors can arise from the interactions of simpler elements in a system. For example, in LLMs, you may have a very large model that is just trained to predict the next word in the sequence, and suddenly it's capable of answering questions, performing classification, summarizing text, and doing a whole lot more than you expected. Emergent properties are often not directly predictable from the individual elements of the system alone. The capabilities or behaviors that emerge from your model are not always foreseeable based on the individual characteristics of your neural network. As the model becomes larger with more parameters, the model may exhibit new behaviors or improve performance in ways that were not apparent in smaller scale versions. An example of emergence in a model like GPT-3 is its ability to write creative fiction, compose music, or generate code, despite not being explicitly trained for these specific tasks. These These abilities are the result of the model's large-scale structural processing and generating patterns learned from vast amounts of data. Now, emergence of models present both opportunities and challenges. While it can lead to the development of highly capable and versatile systems, it also makes predicting and controlling the behavior of these systems more difficult, raising questions about reliability and ethics. When you think about using a large language model for a specific task or application, it's very unlikely that you'll be able to work directly with a foundational model. That's because the foundational model is very broad and is more general purpose. You will want a model that works well based on your expectations, and this is why you need model alignment. Model alignment refers to the process of ensuring that an AI model's behaviors, decisions, and outputs align with human values, intentions, ethical principles, and whatever other task-specific alignment that you want to do. Let's talk about why it's needed first. We've just discussed foundation models and we can see that they are incredibly powerful. We've seen that very large-scale models display emergence, that is, they perform tasks that they are not trained for very effectively and well. However, these foundation models are trained on broad data and may not perform well on specific tasks. For example, if you want a customer support chatbot, you might find that the foundation model is not as polite or receptive to the customer as you want the model to be. And this will be true no matter what the task is that you want the model to perform. Model alignment is the process of ensuring the model's outputs are consistent with the desired goals and values of the users of the model. Goal alignment involves aligning the model's objectives with the intended use case or purpose, which means the model should understand and appropriately respond to the user's requests or queries, achieving the goals for which it was deployed, whether it's answering questions, generating text, or helping with decision making. Value alignment, on the other hand, involves ensuring that the model's outputs reflect human values and ethics. And this is hard because values can vary widely amongst different cultures, individuals, and contexts. With value alignment, we want the model's behavior to follow universally accepted ethical principles and prevent outputs that are harmful, biased, or offensive. The model should also be adaptable to different users and contexts and capable of handling a wide range of scenarios while remaining aligned with ethical guidelines and user intentions. What researchers have noticed is that a pre-trained large language model is not very useful by itself. The results tend to be repetitive and not very helpful. Context, the understanding of nuances of language, pattern recognition, all of these are embedded in the model but still not directly useful. This is why we need to align the model to the desires of human users, allowing the model to generate content that is directly useful and relevant to the user. Now we're familiar with the broad steps involved in creating a large language model. There is model pre-training, that is unsupervised or self-supervised pre-training on a large corpus of input text. There is SFT or supervised fine-tuning that trains a pre-trained model on a labeled dataset for a specific task. And there is RLHF or reinforcement learning from human feedback. RLHF combines reinforcement learning principles with human feedback to guide the model towards the desired behaviors. Now, if you don't know what reinforcement learning is all about, don't worry, we'll be explaining that in detail in just a bit. We've already discussed model pre-training in some detail. This is what is used to create foundation models. This is where models are trained using self-supervised learning, where the labels in the data are automatically or programmatically generated, and models are trained using the language modeling objective, trained to predict the next word in the sequence given all previous words. In this video, we are focused on model alignment, and that includes supervised fine-tuning and reinforcement learning from human feedback. I'm actually going to break these down a little further and add one additional step that is used for model alignment. Model alignment is accomplished in 3 steps. The first is supervised fine-tuning. The second is reinforcement learning from human feedback. And this is the third additional step that I add here, in-context learning or fine-tuning for downstream application. Now, in-context learning comes after supervised fine-tuning and reinforcement learning from human feedback. This is when you are using the model and you want your model to learn from examples that you provide within your prompts. This involves providing the model with a few examples of instructions directly in the prompt or query that you pose to the model. The model uses these examples to understand and perform the desired task within that context. In-context learning has to do with prompt engineering to get the most relevant response from the model. And we'll discuss that separately in another video. At the very end of this course, let's discuss each of these in more detail, starting with supervised fine-tuning or SFT. Supervised fine-tuning or SFT tends to be the first step in the alignment process of large language models. So you start with a pre-trained model, a foundation model that has been trained using self-supervised learning. You then curate a dataset of high-quality large language model outputs to serve as examples of the correct response from the model. This curated dataset is created by human users and serve as examples to give the model what exactly is the kind of response that you expect from the model. This dataset will tell the model the correct set of outputs or actions for a particular set of inputs, and all of these have been provided by human beings. You then fine-tune the model, that is, adjust the weights of the model's parameters using these examples. Now, this is supervised fine-tuning because this method relies on traditional supervised learning techniques where the model learns to predict the provided correct responses. The goal is to align the model's outputs with what is considered appropriate or desired by humans based on examples in the fine-tuning dataset. The model will learn to replicate the style of these examples during the fine-tuning process. This is very useful for aligning models on specific tasks or domains where there is a clear understanding of what constitutes a correct or desirable output. Here is an example of a dataset that can be used for supervised fine-tuning of a large language model. You can see that this example comes from a research paper at Meta. Notice the first prompt about a poem and the expected or correct response. The second prompt tries to get the model to do something that's unsafe. Here we are asking the model to swear at us. Observe that we want the model to refrain from acceding to this request, and that's what the response says. I'm sorry, but I cannot comply with that request, and so on. Supervised fine-tuning is not very different from pre-training using the language modeling objective, where the model is trained to predict the next word in the sequence from the previous words. The main difference arises in the data that is used. In supervised fine-tuning, the data is curated and of a very high quality. Here is another visual representation of how supervised fine-tuning might work. You might ask a question, explain reinforcement learning to a 6-year-old, and the response will include a simple analogy to explain the complex concept of reinforcement learning so that a 6-year-old can understand, and we use many such examples to fine-tune the model. Here is another example. Let's say you're training a customer service chatbot, and the user inputs something like, I can't log into my account, what should I do? And the original output of the model is, try resetting your password using the forget password option. Now you have to admit that this response is kind of blunt, and your organization wants your chatbot to be more polite. With supervised fine-tuning, you can get a customized response from the model. You start with a pre-trained LLM, you feed in a bunch of curated responses which are very polite to all different kinds of questions or use cases that a user might pose to the model. The model will then generate a response that is more aligned with your values. I'm sorry to hear you're having trouble logging in, and then a very gentle response asking the user to try the forget password option. Now, supervised fine-tuning is different from generic fine-tuning. Generic fine-tuning is done to teach a pre-trained model how to solve a specific task, but this ends up making the model more specialized and less generic. The model becomes more of an expert in a particular field and less of a generalist. The model may get better at the specific task that you want it to perform, but may lose its ability to perform other more general tasks. SFT is a core component of aligning language models in foundation models. Because we are fine-tuning the model to emulate a correct style, a behavior, or a correct kind of response, rather than trying to get the model to solve a particular task, the model should not lose its generic problem-solving abilities. When we talk about large language models, we often hear the term RLHF, reinforcement learning from human feedback. This is a more interactive and dynamic approach to model alignment, which combines reinforcement learning principles with human feedback to guide the model towards desired behaviors. All of these terms will be demystified in just a bit. At this point, you have a good understanding of how supervised fine-tuning works. Given a prompt, there are many possible responses and many styles of responses. And supervised fine-tuning trains the model on what kind of response we are looking for. It also allows us to configure the style and tone of the responses. But given a particular response from the model, supervised fine-tuning does not tell the model how good or bad that response is. And that's exactly why we need RLHF. Reinforcement learning involves a system of rewards and penalties. Rewards for actions which move the agent forward towards a better outcome, and penalties for when the agent moves backward towards a worse outcome. In order to understand RLHF, you need to understand reinforcement learning, which is a specific kind of machine learning technique. Reinforcement learning is a machine learning paradigm where an agent learns to make decisions by interacting with the environment with the objective of maximizing cumulative rewards through the process of trial and error. Now, this seems like a mouthful, but it's actually very simple and intuitive, and I'm going to break this down over the next few minutes. One reason this sentence is kind of hard to understand is because there is so much jargon in here. Let's break some of that down. The first thing we focus on is this term agent. Agent here is the learner or the decision maker. And in our training of a large language model, it's the model that's the agent. The agent is just a machine learning model. The way I like to imagine an agent is that it's a robot navigating an uncertain terrain, a terrain that it's not familiar with. Now, this uncertain terrain that the agent is trying to navigate and make decisions within is the environment. The environment is everything that the agent interacts with and learns from. The environment refers to the world through which the agent moves and learns. And in the case of a large language model, the environment can be thought of as the users who are interacting with the model. The model interacts with, responds to, and learns from the input that the user provides. Let's visualize reinforcement learning here. We have two main components, the agent and the environment. And the agent interacts with the environment. At any point in time, the environment is in a certain state, and it is this state that is presented to the user. Let's talk about the state as S of t, where t is a particular point in time. The environment presents a state to the agent at each time step, and this represents the current context. Now, based on the current context, the agent has to make a decision about what it should do. In an LLM, the current context can be all of the interaction that the user has had with the model, and now the model has to decide what text to generate in response to the last prompt that the user specified. Based on everything the agent has learned so far, the agent then goes ahead and chooses some action A of t. Every action or decision made by an agent has a consequence, and every action affects and changes the state of the environment in some way. Now, based on the action taken by the agent, the environment will choose to either reward or penalize the agent. The environment rewards the agent for each action. The size of the reward can be large or small, and it can even be negative. In that case, the reward is actually a penalty. In the case of a large language model, let's say it generates a response, and then you say, oh, thumbs up, this is a great response. That's a reward for the model. Or you say, you know what, this response wasn't really useful, thumbs down. That is a penalty for the model. And this reward or penalty that the environment gives the agent indicates how desirable the action is for the agent. The agent will update its internal policies to constantly receive greater and greater rewards. The objective of the agent is to maximize the cumulative rewards that it receives across all of its actions. And in the context of reinforcement learning, where the agent is the large language model, well, the model will try to produce responses which causes it to gather more and more thumbs ups, that is, accumulative rewards. And now that you understood reinforcement learning, let's talk about RLHF, reinforcement learning from human feedback. The first step is to have human labelers score a data set of prompt completions based on certain criteria. Essentially, you look at all possible responses for a particular input and you say this is the best, this is the second best, and this is terrible. And human labelers will do this for a reasonably large size data set. You then set up a reward model for the large language model. You'll train the reward model to assign rewards for each prompt completion pair. You say that if this is the response by the model, I'll give it like 5 points. If this is the response, that's only 4 points, but this response is 10 points, and so on. You'll thus create a reward model using human evaluations. You'll then use all of these prompt completions pairs to fine-tune the model using a reinforcement learning algorithm. If the model generates a response for which you give it just 1 point, that's the reward for the model. If it generates a better response with say 5 points, that is the reward for the model, and so on. You set up this iterative process of feedback where model outputs are constantly scored by human labelers. Using this reward model, the base model is fine-tuned via this reinforcement learning algorithm. The model here, that is the agent in reinforcement learning, will try to maximize the cumulative rewards and thus improve the quality of its responses based on the scores that human labelers have assigned. The reinforcement learning algorithm that is often used in reinforcement learning from human feedback for large language models is called proximal policy optimization. The PPO algorithm adjusts the model's parameters to maximize the predicted rewards from the reward model that you have set up. This process iteratively aligns the model's outputs with human preferences, and the cycle continues with the base model being repeatedly fine-tuned to align more closely with human judgments. The policy is what the model uses to make decisions, and this algorithm optimizes the policy of the model. Now, the term proximal is because this particular reinforcement learning algorithm updates in a small bounded region close to the previous version. You can think of this as every tweak to the model parameters changes the model ever so slightly. Here is a visualization of how reinforcement learning from human feedback works. Let's say you have a prompt, explain reinforcement learning to a 6-year-old, and there are 4 possible responses. All of these responses are in the right ballpark, but human labelers have specifically assigned different scores to those responses. Based on their judgment, labelers might say the option B is better than C, which is better than A, which is better than B. And the model is awarded rewards based on what option it picks. The proximal policy optimization algorithm will cause the model to maximize the cumulative rewards that it receives, and thus improve the performance of the model based on human feedback. In the final video of this course, we'll talk about in-context learning, prompt engineering and prompt tuning, and we understand the difference between the two. Prompt engineering is the process of structuring text that can be interpreted and understood by a generative AI model. That is, you already have a large language model that has been pre-trained, undergone supervised fine-tuning and reinforcement learning from human feedback, and you're now using it in your day-to-day life, and you want to get the best possible model response. Anyone who's used ChatGPT, Google's Gemini, or Bing Copilot knows what prompting is all about. Essentially, prompts are queries that you pose large language models. Please explain Einstein's theory of relativity in simple terms to a 5th grader. Write code in Python to compute the average of numbers in a list. Write a poem about how programming is fun, should be short and humorous. Prompts can be anything that you want the model to do. Prompting is important because that's how you interact with a large language model to generate the relevant output that will be immediately useful to you. Prompting can also be used to improve the quality and diversity of the generated output. Model responses may not always be inclusive and diverse, and this is actually something that you can control by making your prompt more specific, relevant, and comprehensive. This will give the model an idea as to what it is that you're looking for. When working on scenarios, I often use prompts to generate fictitious names, and I often tell the model to explicitly include names of people from different countries. You're likely aware that large language models can contain inherent biases. Those biases exist in the data that those models are trained on. Using prompt engineering techniques can increase the control you have over the model's responses, improve the interpretability of those responses, and reduce and mitigate bias. Generative models are prone to hallucinations. They may hallucinate knowledge that is not factual or is clearly incorrect. Prompting can guide the model in the right direction by forcing it to cite correct sources, and that helps mitigate hallucinations. Prompting allows you to experiment with diverse types of data and different ways of presenting that data to the language model. Prompting also allows models to know what is good and bad by goal setting. You can incorporate your goal into your prompt itself. I'm looking for a key sentence overview of how black holes work so that I can understand this intuitively. This will eliminate jargon from the model's response. Prompting also improves the safety of the model and helps defend against prompt hacking when users send prompts to produce undesired behaviors from the model. There are, of course, several challenges to interacting with large language models. They're getting better and better over time, but sometimes it may be hard getting the required results on the first try. You may have to go back and forth through the model before you get the precise response you're looking for. Also, if you're working on something complex, it may be hard to figure out the right place to start. What's the question you should ask first so you can move in the right direction? It's also challenging to mitigate bias in the output. Some biases are clear to identify and mitigate, but there might be other biases that are implicit and you may not realize at all the response is biased. Sometimes model responses can be boring and may not cover the wide range of topics that you're expecting in the response. For example, if you're looking for the right technology to use in your software solution and you turn to generative AI, you might want to provide a lot of context for your current use case so that the model gives you the right response. A significant challenge when you're working with large language models is the fact that they work and they work beautifully, but you're often not aware of why exactly they work. And this becomes a problem when the response is inaccurate or maybe just half-baked. Understanding the reason behind the response can be a challenge with prompting. And finally, you would like your model's response to maintain a balance between precision and creativity. You want the model to stick to facts but present them in a vivid and compelling manner. And that balance is often hard to achieve. Large language models are capable of understanding and picking up on subtleties and nuances, and they do matter in prompting. The way you construct or phrase your prompt matters. In fact, every word in a prompt matters. Describe the Taj Mahal versus describe the history of the Taj Mahal. Large language models can disambiguate between the two. We've already discussed the models behind these prompts in a lot of detail. We know that they were trained on large data sets and they use cues from your input to give you answers or responses. Working effectively with large language models involves providing structured and comprehensive prompts. Let's discuss the anatomy of a prompt and what all are the components that make up a prompt. The first is the instruction. This is the core directive of the prompt, and this is what tells the model what you want it to do. Extract keywords from this text. Summarize this newspaper article. I would say that this component is the required component in any prompt. Now, in addition, your prompt can include context. Context provides additional information that helps the model understand a broader scenario or background within which the model should provide a response. Considering that I have just a week's vacation, do you think it makes sense to New York? You are giving the model a backdrop against which to frame its response. Prompts can also include input data, the specific information or data you want the model to process. If you ask the model to summarize text, you have to provide the text that you wanted to summarize. This data can be a paragraph, it can be a set of numbers, or just a single word. You may also specify an output format if you want your model's response to be in a specified form. For example, maybe you want a list of student names in the JSON format. The output format here is JSON. There are certain techniques you can use to make your prompts better. For example, role play. By making the model act as a specific entity, like a historian or a teaching assistant, you can get tailored responses to your queries. As a mathematician, please explain the intuition behind Black-Scholes formula. That's the example of a prompt where you ask the model to play a specific role. Next is iterative refinement. When your query is complex and may require back and forth with the model, it might be best to start with a broad prompt and gradually refine it based on the model's responses. This process will improve your prompt till you've gotten exactly what you need from the model. Another is adding constraints. The model's response will be more relevant if you're specific about your constraints. For example, you might say use simple language, don't use jargon, or use technical terms. Positive constraints generally work better than negative constraints. Do use simple language, do not use complex language. And finally, you should be using the model's output to inform and adjust your subsequent prompts. The dynamic interaction ensures that the model's responses align more closely with your expectations. There are certain advanced techniques that you can use in prompting as well. Zero-shot prompting involves providing the model with a task it hasn't seen during its training. This tests the model's ability to generalize and produce relevant outputs without relying on prior examples. Sometimes a model will work better with examples. That's when you use few-shot prompting. Here the model is given a few examples or shots to guide its response. By providing context or previous examples, the model can better understand and generate the desired output. For example, you might say, these are the kinds of books I like to read. Please recommend some other books like these too. That's an example of few-shot prompting. There is also chain of thought prompting. This is useful for more complex tasks where you guide the model through a series of reasoning steps. You break down the complex task into intermediate steps or chains of reasoning, and the model can thus achieve better language understanding and more accurate outputs. Generated knowledge or augmented knowledge prompting prompts the model to generate the relevant facts for completing the prompt and then proceeds to complete the prompt. This results in higher quality responses as the model can be trained on relevant facts. Prompt tuning is different from prompt engineering. This is where you use the most effective prompts or cues to train generative models in a very task-specific context. Prompt engineering gets you the best possible response from the model. Prompt tuning is more about improving the model for a specific task. Prompt tuning is a technique where a small set of additional trainable parameters, that is a soft prompt, is optimized to guide the model for a specific task without altering the underlying pre-trained model itself. The soft prompt is trained on a task-specific dataset, effectively teaching the model to perform a particular task or understand a certain type of input better. This process is far less resource-intensive than full model fine-tuning. Prompt tuning can involve adding keywords, phrases, or structured instructions that the model has learned to respond to during its initial training phase. Prompt tuning allows users to adapt a large model to a specific task with relatively few additional parameters, maintaining the flexibility of the base model while tailoring it to specific needs. Prompt tuning might involve fine-tuning a subset of the model's parameters, often those associated with the prompt itself, to improve the performance of specific tasks. Whereas prompt engineering is all about refining and crafting the right prompts for relevant responses. And this brings us to the end of this course on GPT models. We started this course off by introducing the realm of generative pre-trained transformers, GPT, and the foundational models that underpin the GPT-N series. We understood the underlying meaning behind each of the terms that the GPT represents. We learned that these are powerful large language models that perform incredibly well on natural language processing tasks. highlighting the importance in the development of advanced GPT-N series models. These models, built on vast amounts of data, have set the stage for unprecedented advancements in natural language processing, enabling a wide array of applications from automated text generation to sophisticated dialogue systems. Next, we learned about the transformative paper Attention is All You Need and the subsequent development of the transformer architecture, which serves as a backbone for GPT models. This segment of the course focused on understanding the mechanics of the transformer architecture, particularly its reliance on self-attention mechanisms to process and interpret sequences of data. The transformer's innovative design allowed it to effectively manage long-range dependencies in text, facilitating more coherent and contextually relevant text generation. We saw that this understanding is crucial for grasping how GPT models achieve their remarkable performance in generating human-like text across diverse tasks. Finally, he explored the intricacies of the GPT model itself, starting from its pre-training on vast datasets to capture a wide spectrum of human language patterns. We discussed the importance of understanding foundational models and their role in pre-training GPT models to serve as a versatile base for various applications. This course covered the methods used to align these models with specific tasks, including supervised fine-tuning, reinforcement learning from human feedback, and innovative techniques like prompt engineering and prompt tuning. These strategies are pivotal for tailoring GPT models to fulfill specific tasks or requirements, enhancing their effectiveness and utility in real-world applications. In conclusion, the foundations we've built so far in this course provide a comprehensive understanding of the GPT models and their underlying technologies. These models, built on vast amounts of data, have set the stage for unprecedented advancements in natural language processing, enabling a wide array of applications from automated text generation to sophisticated dialogue systems. Next, we learned about the transformative paper Attention is All You Need and the subsequent development of the transformer architecture, which serves as a backbone for GPT models. This segment of the course focused on understanding the mechanics of the transformer architecture, particularly its reliance on self-attention mechanisms to process and interpret sequences of data. The transformer's innovative design allowed it to effectively manage long-range dependencies in text, facilitating more coherent and contextually relevant text generation. We saw that this understanding is crucial for grasping how GPT models achieve their remarkable performance in generating human-like text across diverse tasks. Finally, he explored the intricacies of the GPT model itself, starting from its pre-training on vast datasets to capture a wide spectrum of human language patterns. We discuss the importance of understanding foundational models and their role in pre-training GPT models to serve as a versatile base for various applications. This course covered the methods used to align these models with specific tasks, including supervised fine-tuning, reinforcement learning from human feedback, and innovative techniques like prompt engineering and prompt tuning. These strategies are pivotal for tailoring GPT models to fulfill specific tasks or requirements, enhancing their effectiveness and utility in real world applications. In conclusion, the foundations we've built so far in this course provide a comprehensive understanding of the GPT models and their underlying technologies.
काय?
Is the blueprint behind intelligent, goal-driven AI systems. It explains how these systems understand their surroundings, set goals, make choices, take action, and learn over time, turning them from fixed models into flexible, interactive ones. In this course, we'll explore how agentic AI systems work. Not just what they do, but how they think, act, and learn. We will begin with a visual walkthrough of how agentic systems work from start to finish. We will discover how agents interpret messy real-world inputs, extract context, and prepare for intelligent action. We will learn how memory gives agents a sense of continuity, helping them stay relevant and improve over time. We will also discuss how agents generate plans, sequence tasks, and make smart decisions step by step. Then, we will explore how they use tools and how agents connect with digital environments. Additionally, we will explore feedback loops, how agents learn from results and refine their behavior. Finally, We will compare different architectural styles, from simple reactive agents to adaptive, learning-based systems. By the end of this course, you will have a deep understanding of how modern agents operate and how to think like one. You say, "Can you book me a table for dinner tonight?" Seems simple, right? But for an AI agent, this request launches a chain of intelligent steps, interpreting your need, searching options, making decisions, and acting on your behalf. In this video, we'll walk through how an agent thinks and acts, step by step. We will now look at request to reservation using an agentic flow. This is the multi-step process where the agent can take action, process requests, and adapt, executing the task that might otherwise take a while to resolve. The agent receives your request and begins its loop. Perception, what are you asking for? Memory, what do you like? Any past favorites? Planning, what's the best way to get this done? Tools, check and book via a reservation API. Feedback, was the booking successful? Did you like it? Let's walk through each of these in context. First, the agent receives your request, book a table tonight, and parses it into structured meaning. Intent, restaurant reservation. Time, tonight. Then it looks into memory. You usually eat Thai, prefer 7 p.m., and have previously dined at Siam Kitchen. With this context, the agent is ready to plan. What preferences would you want an AI to remember for your convenience? Next, the agent makes a plan. Step 1, search Thai restaurants near you. Step 2, check which ones have availability at 7 p.m. Then it takes action, connecting to a restaurant booking API like OpenTable or Zomato. It filters and selects the most suitable option. Next, the agent books your table successfully. Later, you give it 5 stars. That's feedback, a strong signal that the choice was good. Next time, the agent may prioritize similar restaurants or time slots, gradually improving its recommendations. In this part, we will now reflect on our experience. Think about your recent interaction with a digital assistant. What could it have learned from your feedback? As we wrap up this part, let's consider what makes the interaction possible. The magic behind this experience comes from powerful components working in harmony. Perception to interpret your request, memory to recall past choices, planning to decide how to act, tool use to take action, feedback to improve over time. In the next videos, we'll explore how each of these works in modern agent frameworks. It must first be able to understand. This begins with perception, the process of transforming raw inputs like user messages, triggers, and data into meaningful information. In this video, we'll explore how agents perceive their environment and turn it into structured knowledge that supports decision-making. Imagine you told your assistant, "Order me something spicy." What does that mean? A taco? A prank gift? Something risky in life? Without perception, even humans would fumble. You may wonder, is spicy referring to food, a challenge, or a joke? Even humans pause to ask such questions. For agents, perception is the skill that helps them to disambiguate, extract intent, and prepare for action. Perception in agents involves three key subtasks. First, it extracts intent and key entities, just like natural language processing.
चांगलं आहे हे.
systems.
नाही लागत मी अख्खी
Then,
खाल्ली
it
आहे बस.
enriches this input using memory.
अरे ते तसंच असतात ह्या.
Finally, it normalizes the result into a structured format.
हे नाही एवढी.
Let's now unpack these in more detail.
हे दिवसाचं नाही आहे उघडं
Perception
ते.
pipeline looks like inside of an agent. First,
इकडं
the
ते ऊन
system
लागतं.
captures the input. This could be a user message or a system event. Then it passes through an interpreter, which might use a large language model, LLM classifier, or keyboard extraction to detect intent and understand the input type. Context clues are here, either from the agent's memory or the current environment. The input is then cleaned and validated, ensuring it fits expected formats or logical rules. Finally, the system reformats the input into a structured state, like a task object or plan request, ready to be handed off for planning or action. This raises an important question. What powers perception? Under the hood, perception often combines LLM prompts, a memory-based search for vector memory, and domain-specific possibilities. Think of it like a mini translation engine, converting messy human input into clean agent instructions. Let's now take a moment to pause and reflect on something important. Not personalizes interactions and enables learning and feedback. Agent memory is often organized into three distinct layers, each serving a different purpose in how the agent understands and adapts over time. Short-term memory is like a mental whiteboard. It holds the most recent interactions or steps in a conversation. This allows the agent to maintain continuity in a session, follow multi-step instructions, and avoid repeating questions. Long-term memory acts like a knowledge vault. It stores persistent information, things like your name, preferences, past choices, or domain facts that the agent has learned over time. This helps the agent personalize responses or make informed decisions across sessions. Episodic memory is more like a journal. It logs specific experiences, such as what the agent did, when it did it, and what the outcome was. This kind of memory enables post-analysis, learning from success and failure, and even storytelling or debugging. Together, these memory types form the cognitive backbone of the agent, helping it stay coherent, relevant, and continuously improve. Let's look under the hood at how memory powers the agent's intelligence. When new input arrives, the agent first checks if memory is needed. Based on cues like user identity, past history, or missing context, it then queries its memory system to retrieve relevant past data. This could include previous interactions, tool outputs, or important facts. This search might use vector similarity, metadata tags, or knowledge graphs to find the most useful memories. Once retrieved, the context is filtered, cleaned, and injected into the current reasoning process, often guiding its own perception and planning. Finally, after the task is complete, the agent stores new insights or outcomes, continuously enriching its memory for the next run. In this part, we will reflect on learning from experience. It's important to note that memory isn't static, it's adaptive. For example, agents can log tool usage and task outcomes, and tag success and failures for future review. Furthermore, advanced systems use memory to reflect, retrain, or adjust strategies, turning experience into improvement. Before an agent can reason or act effectively, it needs access to the right information at the right time. That's where memory plays a critical role, not just as storage. Smart agents don't record everything. They remember selectively. Good memory design means storing what's relevant to the task, user, or goal, not every input or step. Some information, like user intent, is only needed for a short time. Other details, like preferences or past actions, are valuable long-term. Distinguishing between the two makes memory more efficient. It's not just about storing memory, it's about finding the right memory. Intelligent retrieval lets agents surface context at the right moment, enhancing continuity and reasoning. Effective agents don't just store, they adapt. By learning from feedback and outcomes, memory can grow more relevant over time, improving behavior and personalization. About how agents decide what to do, when to do it, and in what order. Imagine telling your AI to book a team meeting. It finds a room and books it, but you're double booked. Why? It didn't plan well. Planning means sequencing steps based on dependencies, tools, and available context. Without thoughtful planning, even the best perception and intent recognition can fall short. In simple tasks, reactive response might be enough, but real-world tasks often involve many moving parts. They're not just one-step commands, they need structure. The order in which actions are taken can make or break the outcome. That's why agents must reason through each step and assign the right tools, or even other agents, to get the job done effectively. Planning sits between perception and behaviors. Once the agent understands the input and pulls relevant context from memory, it needs to decide how to proceed. That's where the planning engine steps in. Using structured input, the agent queries a planning module. This could be a reasoning chain, a rule-based planner, or a policy model. It decomposes the main goal into smaller tasks, arranges them in modular order. It then prioritizes and orders the subtasks, maps these steps to the relevant tools or other agents, and incorporates required constraints and policies. The control logic and fallback strategies are defined, which gives a detailed executable plan. This plan is then passed on to the action executor module. When it comes to planning, agentic AI systems have multiple strategies, each suited to different levels of complexity and flexibility. Rule-based flowcharts are the simplest. They follow fixed logic trees, like if user says X, then do Y. These are predictable and easy to debug, but quickly become rigid or brittle when tasks get complex. Chain of thought prompting adds a layer of intelligence. Here, the agent uses a language model to reason step by step in natural language, often simulating human-like thinking to figure out what to do next. This enables more flexible, context-aware decisions, without hard-coding every path. At the highest level of sophistication, we have dynamic planning graphs, such as those created using RankGraph. In this model, each task or decision is a node in the graph. The agent can choose paths dynamically based on real-time data, feedback, or outcomes. This allows for conditional branching, looping, and recovery mechanisms, much like how humans revise plans on the fly. In short, flowcharts are predictable but rigid. Chain of thought is flexible but less structured. Planning graphs are modular and adaptive, ideal for complex, evolving workflows. It's important to be aware of common pitfalls when it comes to planning. For instance, agents can sometimes fail by skipping the planning phase entirely, diving straight into execution without a clear roadmap. Another common issue is using the wrong tool, often because the goal wasn't broken down properly. Additionally, overlooking prior steps that have already been outlined can lead to misalignment or failure. That's why good planning is like scaffolding. It keeps everything aligned, supported, and ready for successful execution. Planning in agentic systems doesn't operate in isolation. It actively pulls from memory to make informed decisions. When an agent receives a goal, it first consults relevant past interactions, user preferences, or task history stored in memory. This contextual knowledge helps it understand what's already been done, what worked or failed previously, and how to proceed effectively. Next, the agent decomposes the goal into smaller tasks, sometimes in a linear sequence, sometimes branching out depending on dependencies. For each subtask, it decides whether it can act internally or needs to delegate, either by calling an external tool, triggering an API, or handing the task off to another agent in the system. The output from planning isn't just a list. It's often a structured execution payload that tools or agents can act on directly. Critically,